Recorded is rolling. It is Friday, October 17th. So we're going to finish this rotational kinematic lab that we started yesterday. Now, on the back side of this page is a different lab that also involves a turntable. So, you guys, at the end of class today, go ahead and hold on to this paper, and then next week we'll do this one on the back. Right, and then I'll just put both grades in the grade book next week. Okay. We'll probably have some time at the end of class to start those textbook puzzles also. Right, so for you guys, that's the ones that look like this. So I'll see if I can fit in one or two of those at the end of class today. And don't worry about AP classroom because that's not you guys. Okay. All right. So you guys got what we're doing? Okay. So we got this far on the slide yesterday. So here's a recap of what's going on. Okay. So I have this turntable. You give this a spin. Okay. Right, I see these three different points here. Three different kind of motion. Okay. Now, if I just focus on one of them, okay, say this guy on the outside. Okay. Now, the first number I had you guys record was the distance from the center. Now, mine says 11 centimeters. So let me go ahead and put Roosevelt at 11 centimeters, just like he was yesterday, right, from the center. Okay. Now, for you guys, you got a different number. That's okay. You go 8 centimeters, 9 centimeters, 12 centimeters, whatever. Okay. But then there were two halves of the story. The first half is give it 3 revolutions. The second half is you let it go and let it slow to a stop. Okay. Now, those 3 revolutions, you were going to time on a stopwatch. We did all that already. And then when it slows to a stop, you take out the protractor and measure how far did it go come to a stop. So it went like this. Right. So with stopwatch, you start, you go 1, 2, 3, and then let it go. And it will slow to a stop, something like that. Right? Now, as you saw it right in front of me, that actually did one complete revolution plus a little bit more. And yesterday I remember it went 350 degrees, which was just short of one revolution because it's a little bit different. Right? So yesterday I did 3 revolutions. It took 6.8 seconds. And we said, oh, well, if 3 revolutions, guys, how many radians? How many radians are in one revolution? Okay, so 360 degrees. Okay, so one revolution equals 360 degrees equals how many radians? 2 pi, 2 pi. So if you do 3 revolutions, that's where the 6 pi comes from, 6 pi radians. Okay. If that happened in, I still got the same number on my watch from yesterday, 6.8 seconds. This is exactly the time. That's the last time I used a stopwatch. If you divide that out, then we get radians per second. Right? Radians per second is radians per second. Right? That's how fast it was rotating. As long as I kept it constant angular velocity, it was pretty close. Pretty stuff. Okay. I then allow it to slow to a stop. Now, I measured 350 degrees, but I did have to convert that to radians. And for you guys, you had whatever the stopping angle was. You can measure that with a protractor also. Right? Walked around class, make sure everybody had numbers. That looked pretty reasonable. Okay. How do you convert from degrees to radians? Like how many degrees is equal to how many radians? What's one way to convert it? Could you do 360 degrees is equal to 2 pi radians? Right? Could you do 180 degrees is equal to pi radians? I may have done it that way. And somebody earlier today said, oh, I know 1 radian is about 57.3 degrees. Could use that too. Right? They're all about the same ratio. Same ratio. Right. So I got the stopping angular displacement in radians, like how far did it turn coming to a stop? It's sort of like degrees, but it's radians. Okay? And then from there, we were able to make some calculations because we broke out these kinematic formulas and said, okay, so here's like angular displacement as a function of time and so on. Okay? Now, if you look at this very last one, if you know it slows to a stop, guys, slows to a stop, what's the final angular velocity? 0. So put a 0 right here. Okay? And at the beginning of that interval, the beginning of the second half of the story, when you took your hand off, the angular speed was however fast it was going, which is this number here. You see it? That's how fast it was rotating. Right? Second was right here. Okay. And you know the angular displacement that it took to come to a stop, because that's where you broke up the protractor, converted to radians, and where that number right there. It goes right here. Okay. So we got this, and this. Could you calculate this alpha? Did you guys do that? Okay. We did that yesterday, right? We did that yesterday. Okay. And that's how I got this number right here, negative 0.63, and that's radians per second squared. Now that was definitely negative for everybody because it was slowing to a stop. Okay. And I did print the negative number just to for sure emphasize that that number's going to be negative. Uh, okay, is that right? And then we did one more thing yesterday for the bell ring. That was we took the alpha that we now know and ran that into the second equation because now you know the alpha here. You just found that. Okay? Omega final is still 0. Omega initial is still what you got from the first half of the story. We just found alpha, and you can solve for the stopping time, right? Solve for the stopping time. Right. So we did that too. And the number I got was 4.4 seconds. Now, again, that was just me doing it. So as soon as I let it go, I saw it kept rotating, but because of friction, it slowed to stop. Yeah, it took about 4.5 seconds. Like, that looks believable. I think if I had a second stopwatch and I timed it, it'd probably confirm that. I mean, that looks believable, right? Pretty close. Right. All right. So you guys ready for next part of the process? Okay. Next part is we're gonna make some graphs. Let's make these three graphs over here. So what's angular displacement as a function of time, angular velocity, and angular acceleration. So let's label these axes. So the vertical axis, I got angular displacement, that's theta, that's gonna be in radians. Okay, and then that's as a function of time in seconds. The second one's gonna be angular velocity in radians per second, also as a function of time in seconds. And this last one here, that's sort of an upside down type graph, it's negative, is angular acceleration, that's alpha. That's going to be in radians per second squared as a function of, again, time in seconds. Okay. So yeah, it's really important to have your axes labeled. What variables are you talking about? What units are you measuring those variables in terms of? Because when we draw these graphs, which we're about to do, your graphs communicate information to whoever's reading your graphs. They say, okay, there's a relationship between this and it looks like this, and right? But they have to know what they're looking for. So let's start with this velocity type graph, this angular velocity, because I normally start with the middle graph and then branch out from there. I've been doing that for a few months now. Right, so um, I did give you one time, actually, I did this on all three graphs. I gave you that time where you go from the first half of the story to the second half of the story, go from constant angular velocity to letting it slow to stop. So I'll go ahead and write in that time for mine. Now mine is 6.8 seconds. Remember, I was initially rotating it at constant angular velocity for 6.8 seconds. That's going to be true on all these 6.8 seconds. Um, so while I'm rotating it at constant angular velocity, what does the angular velocity as a function of time curve look like? What shape? It's constant angular velocity. It's not speeding up. It's not slowing down. Yeah, straight flat line. Just straight like that. It's just a flat line. And I can put a value on that. So I'm looking at this number right here. I was getting about 2.77. That's radians per second. Right? That's how fast it was rotating. Because it went 6 pi radians at 6.8 seconds. Divide that out. It's 2.77 radians per second. Yeah, that's how fast it was rotating. Right? Right, true. Now you guys, of course, have a different number, but it's whatever number's in this box goes right there. Right. Okay. Then the second part of the story, guys, where it slows to a stop. Guys, slows to a stop. What does slows to a stop look like on for velocity versus time? Well, it's going to a stop. What's the final velocity?
Zero.
Yeah, zero. 0 radians per second. Somewhere down here. Now, if I want to make this sorted to scale, I know for my turntable, this took an additional 4.4 seconds, like the second half of the story, we're slowing down 4.4 seconds. Now, on this time axis, I just say, well, that's in addition to the original 6.8 seconds that it was going constant angular velocity, 11.2 seconds. So the entire story, no, I'll put 11.2 seconds right here. The entire story from beginning to end was, for me, 11.2 seconds, right? About 6 or 7 seconds of spinning it, and about 4 or 5 seconds of slowing down. That's it. About 11 seconds altogether. Okay. And you guys said this part of the graph looks like what? Just like that. Straight shot towards there. Okay. Hasn't that been the case ever since August? That velocity versus time graphs, they tend to form like straight lines. There's nothing curvy about them, anything like that. Okay. That's one of our default assumptions in the class, just to simplify things a little bit. Okay. Although it's probably pretty close to the truth. Okay. But if you saw this play out in real life, like, yeah, that looks just like it should look. If you watch the disc like slow at constant rate. So you guys give us that. All right. Let's do angular acceleration. This one at the bottom, angular acceleration. So the first half of the story, where you were rotating at constant angular velocity, what was the angular acceleration? Angular acceleration. Okay. Here, I was going to bring this out later, but this might be helpful now anyway. Guys, angular acceleration is what we're interested in now. So we got these three kinds of acceleration we're juggling, but really we're just focused on this pink one right now. So, here, okay. So rate change of angular velocity. Well, guys, if it was a constant angular velocity, is it changing? No. So the rate change would be equal to zero. Yeah. Or you could have also said that from the slope of the velocity versus time curve. Okay? Like if the slope on velocity versus time is zero, then the acceleration coordinate is equal to zero. It's just zero. So, okay. Now, again, that was only while you were hand powering it to keep it at constant angular velocity. Okay? But as soon as you took your hand off, it started to slow down, didn't it? It would slow down at a constant rate. Because the constant rate that it slowed down, wouldn't that be the slope of this angular velocity versus time graph? The slope? You guys all see a negative slope down here? So, like so. I can call that alpha. Okay? That's that property of that graph. Okay? So on the as a coordinate on the alpha versus t graph, how do you finish out the rest of the story? We'll take it all the way to, for me, to be 11.2 seconds. Okay? What's the rest of the story look like? Is it a flat line? Yeah, just like that. And the value of that flat line is this number right here. So for me, it's negative 0.63. That's radians per second squared. Like that.
Why would it be a flat line?
Yeah, because it's slowing down at a constant rate. So for angular velocity versus time, it starts out spinning fast and it goes slower, 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 slower until it finally comes to a stop. But the rate that it slows down should be pretty consistent. It's just losing the same number of radians per second per passing second. Yeah, so it's just a constant acceleration. Yeah, yeah. Kind of like if you toss a ball off a cliff, as soon as the ball leaves your hand, its center of gravity is going 9.8 meters per second squared. Not a constant number. Doesn't matter how long it's been falling for. I guess it. Okay. Now the trickiest one here is probably the angular displacement versus time. You guys ready for angular displacement versus time? Okay. Uh, I'm gonna take a trip around the room. I'm gonna see. I'm gonna challenge you guys here. Who can correctly draw this top graph? Remember, there's two halves of the story. So you've got everything before 6.8 seconds and everything after 6.8 seconds, or whatever time on your paper. Might be two little bit different shapes, but can you guys figure out what that top graph will look like for the whole story? Walk around, see if anybody can figure this out. Okay. If you have a pencil, then that might be good because if you get it wrong, you can just erase and redraw it. But can anybody figure out what that top graph is going to look like? Oh, where's your map? Where's your map? Oh, here. Okay, so uh, does anybody think they know what this is going to look like? Right. How about this? Let's start this at point zero. Let's say at the beginning of the time interval, it hasn't like, moved anywhere yet. That we're considering. And then, okay, it's rotating. No, let's say it's going like counterclockwise. I'll consider that positive direction. I think that's the way I was doing it anyway myself. Okay. And as time passes, isn't it rotating further and further and further? Right? It's like accumulating angular displacement. Right? Like, here, give you guys a visual. Right, so you can watch this go around. Huh. Right. Like here, if I start it right here, sorry, let's go right here. It starts on the x-axis. Right, then let's see, that would be 2 pi radians, 4 pi, 6 pi right there. Right. So 3 revolutions would be 6 pi radians. Right. In fact, I know it has to get to 6 pi radians during the first interval. It has to reach that point. Okay. Because if it was reaching that point from 0 to 6 pi radians, 6 pi radians, at a constant angular velocity, what kind of connections between those dots?
Straight line.
Yeah, straight line. Zip. Just like that. It's a straight line. Okay. Then you take your hand off and it slows to a stop. Now I know mine stopped here at 11.2 seconds. Well, after 4.4 additional seconds, we calculated that. So 11 seconds altogether. Guys, what does slowing to a stop look like?
Curve. Curve.
Yeah, curve which way? Because is it still
Go down.
moving in the forward direction?
No.
Or does it turn clockwise and go backwards?
I'm flipping.
Still goes forward. Still goes forward. Okay. Okay. All right. So if I pick up here and it was rotating, I take my hand out. It's still moving in the
Yeah.
forward direction. Right? As it didn't do this, it's not like, okay, I'm spinning it, and I take my hand off and it's gonna go backwards. Oh, no, it didn't do that. No, it kept going forwards, slower and slower until it finally came to a stop. It kept going in the counterclockwise direction I sent it initially. Okay? So it's still going forwards. Still going forwards, just slower and slower and slower. How do you guys draw forward, slower, slower, slower? That shape right there. Hook a little parabola on it. Or that is a parabola, isn't it? With a vertex, bing, right at the very top right there. Little piece of parabola first down the cap. Okay. And I know I have a poster for this one too. Here it is. Here it is. Okay. Actually, it's just this right here. Now, this is only the second half of the story. This is the slowing to a stop half of the story. Okay. And so angular velocity, zoop, straight shot towards zero. Angular acceleration, constant negative. And this is what you just drew is angular displacement. It's still going for it, still accumulating angular displacement, but slower, slower, slower till it comes to a stop. And there's the vertex of that parabola right there. Just like that. Hey, guys, what if I change the story a little bit? What if I change this to a car is moving in a straight line, braking to a stop, and it changes to X, V, and A? You guys remember that? Car brakes to stop. And the curves looked exactly the same. Right? Because if you're moving forward in a car and you hit the brake, you're still moving forward, just slower, slower, slower. So X versus T also looks like that. Yeah. Yeah. Let's go and all the linear values. Right, so let's do linear. Okay. So everything we've talked about so far and all the numbers recorded have to do with angular motion. Okay. Let's get all these guys back on here. Okay. So guys, do all three of these coins right now have the same angular motion? Are they all doing the same number of radians turning, the same radians per second, and so on? Yeah, they all have the same rate angular motion. But they're all at different linear values from the center. Right. So let's look at Lincoln here. Because in terms of like number of meters moved, how far is Lincoln moving?
Yeah.
Yeah, zero. He's not moving anywhere. Okay. Now Roosevelt, I see, has like there's some circumference here to go all the way around. Okay. And Washington, has twice the radial distance out approximately. I bet Washington's moving twice the linear distance and so on. If you were in a car, guess what if these were three cars on a big old field? They're all driving in circles. Okay. What do their odometers say? So Lincoln's odometer always says zero. It's not never going anywhere. He's just kind of sitting there. Okay. Maybe Roosevelt's odometer says like a mile, and maybe Washington's odometer says 2 miles or something like that, right? Okay. So yeah. Okay. And the formulaic connection, well, that's these right here. Okay. So if you have angular values like angular displacement, velocity, acceleration, okay, theta, omega, and alpha, and you very simply multiply by your distance from the center, all that radius, r, I'll tell you all the tangential linear values. So here's the odometer reading on the car. That's x. Here's linear speed. So what if a cop on the side of the road pulls all the radar guns, sees how fast your car's going? That's his v right here. Yeah. And Lincoln, of course, would always read zero. Okay. And then you can also do that for acceleration. Get like a tangential type acceleration. Okay. So let's try this here. Okay. So that distance moved. Well, I know what theta is. I gave it, actually, that's the same for everybody. Isn't that 6 pi? 6 pi radians? Okay, so everybody has 6 pi radians. Go ahead, do your calculator, type 6 pi. Everybody can do that because I gave everybody 6 pi radians. Right? Now, if you multiply that by your radial distance from the center, mine's 11 centimeters, that'll tell you how many centimeters total that coin moved. Like going around the circumference of a circle. Right? Actually, I did 3 of those. So mine is 207. 207. Okay. Great. Which, by the way, guys, how many meters is that? How many meters? Is that like 2 meters? Yeah, that's over 2 meters. Woo! That's actually a pretty good distance, right? Right. Um, how about how about tangential velocity, like a speed? Like if you had a speed gate, you're going through a speed gate, and you measured it. So can I take this? Or let's do this one right here. Here's my omega. Now mine is 2.77 radians per second. Okay, and you guys have whatever you have, right? 6 pi divided by however many seconds gives you how many radians per second. Okay, so we did that yesterday. Okay. Multiply that by however many centimeters radius, mine's 11. I'm getting 30.5 it rounds to. 30.5. Around the nearest 10th place. And that's centimeters per second. Because of R is in centimeters, the speed in centimeters per second. Yeah. And keep in mind too, all these angles are in radians and radians per second because that's the only way you can apply these formulas. Right? You can't put in degrees or revolutions or anything like that. It's got to be radians. All right. How about how about the stopping distance? Can I take my 6.1 radians here and multiply by 11 centimeters? Oops. You get about 67 centimeters thereabouts. Right. And how about acceleration? Now, acceleration is this last one. So take your angular acceleration, which we got right here. We calculated that near the end of class yesterday, alpha, multiplied by the radial distance, and I'll give you the sort of like tangential type acceleration. So for me, it's negative 0.63 times 11. I'm looking at negative 6.93 centimeters per second squared. That's the rate that it was slowing down, like in a linear sense, as if there was a car that was actually hitting the brakes and moving in a straight line, or even turning the steering wheel, but you're considering sort of the linear type motion. Right? Right, that there? Yeah. Right, so bring this in here. So at this point in the class, you're juggling three different types of acceleration that mean different things with different types of units. So the first type of acceleration you guys learned is this green one right here. It's just the rate change of velocity. So if you're in a car going in a straight line, speeding up, slowing down, change of velocity over change of time. Okay, that's the very first one you learned like a few months ago. Okay. Uh, then with this turntable lab, we're interested in angular acceleration, call that alpha, the rate change of angular velocity, is this is going to be in radians per second squared. So the green one here is in meters per second squared. This red one's in radians per second squared. Guys, have we anywhere on this lab yet talked anything about centripetal acceleration? Centripetal? That's something different. Is that's the inward acting acceleration uh, that comes from centripetal force. If you take centripetal force and divide by the mass of the coin, right? It's sort of like a G force. Like if you're a ladybug that's landed on that coin, now you're going around. Whoa, whoa, whoa. It feels like there's sort of a outward acting gravity. Really, what it is it's like an inward acting force, maybe friction or something like that. That's holding you in a circle. Okay, right, so something like that. Let's let's do a centripetal acceleration. Because I showed you guys two different ways to get that. And one looks a lot like your last lab, v squared over r. Another way is omega squared times r. Let's try both of those. So I'm going to put that right here. I'll say a sub c equals, and I'm going to do this two different ways. Okay. So let's do omega squared times r, and later on we'll do the other method. So here, all I'm doing is this right here, omega squared times r. You guys see your omega, and this is for the first part of the story, the part where you're going constant angular velocity. Okay, you guys got that? So here's my angular velocity. I'll type that in the calculator. It says to square that, so I'm going to square that. Right? So you guys just squared your angular velocity, and then multiply by the radial distance. So in my case, 11 centimeters. Okay. Now this is when I hit enter, it's going to tell me the centripetal acceleration. This sort of like feeling a g-force pushing you to the side because you're in a rotating frame of reference. Okay. 84. It's telling me 80. Well, I'll just round it to the nearest whole number, and that would be centimeters per second squared. So 84 centimeters per second squared. Now, what about this other method? V squared divided by R, which is very similar to what you guys did out loud with the Play-Doh canisters. So here's my V, 30.5 centimeters per second. If I square that, divide by 11 centimeters, it should be the same number or very close because they've been rounding a little bit. Should be same number or very close. Yeah, it's the same thing. 84, well, around to 85 centimeters per second squared. Okay. So while I had constant angular velocity, there was an inward acting force that provided this centripetal acceleration that you can quantify this much. Okay. Guys, what is Earth gravity in centimeters per second squared? How many? Was it 980? You guys remember that? You've used that on some of your labs in the past, like Atwoods and stuff. 980 centimeters per second squared. Well, if this is like 85-ish, wouldn't that be less than 1/10 of a G? Yeah. So if you were that ladybug on say, my turntable flying around, you would definitely feel full Earth gravity pulling you down. Okay? And you would also feel like this sort of side gravity force that popped up is that would really it's just this effect. Right? But it would feel like something like almost a tenth of Earth gravity. Okay? Yeah, that's what that means. All right. Okay, let's set these average values right here. So let's just take omega average for the second half of the story. Okay. Guys, would omega average just be like the something about the midpoint of this line is slowing to a stop? Is that I mean this is probably the most straightforward way to get it. And isn't that half of however fast it was spinning to begin with? Now mine is 2.77 radians per second. So divided by 2 gives me 1.38, 1.38. Okay, and that's radians per second. Okay. And then to convert to a linear value, all I have to do is multiply by r. In my case, 11 centimeters. So say times 11, that gives me 15.2 centimeters per second. That's our average value. All right, finally, let's make these three kinematic graphs for, okay, guys, the average linear velocity, all you do is take your average, did you get the average angular velocity? Yeah, and just multiply by your radius. Okay, you're just doing this right here. 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 All right. So let's do how far in centimeters as a function of time and seconds. How fast in centimeters per second, like radar gun speed as a function of time and seconds. And let's do, now this will be tangential acceleration in centimeters per second squared as a function of time and seconds. Okay. So just to specify, this very last acceleration is not angular because we did that over here. And it's also not centripetal, but well, I just didn't make a graph of that. Okay. All right. So we have all the numbers right here. We just take these numbers and translate it into graphs. So the time is the change time is still the same as it was before. For me, it's 6.8 seconds. So that's 6.8 right here. The end time is the same as it was before. So for me, that's 11.2 seconds. 11.2, 11.2, 11.2. So that's the same as before. Okay. Hmm. Now what? Okay. So let's start with the velocity versus time graph. Okay. Um, Now here's your instantaneous speed, your tangential velocity, you could say, during the first half of the story. So for me, it's 30.5. That's centimeters per second, 30.5 centimeters per second. Now, guys, was that a constant speed while it was rotating at a constant angular velocity? Yeah, it's a constant speed. It's a constant tangential velocity. Now, I want to be careful about saying constant velocity. That would not be the case because it's changing direction. Okay, so there's an acceleration involved. Right? I can say constant speed or constant tangential velocity. Okay? And then by the time I get to the very end, to the end of the second half of the story, it's not moving at all. So it wouldn't have zero final linear velocity. Okay? And what kind of shape connects from here to here? Straight line. Zip. Straight line. All right, break to stop. How about linear tangential acceleration? Right. So while it was going at constant angular velocity, was it speeding up or slowing down? And so what was the tangential acceleration? Zero. Right. That's they put space for that over here. No, not in the table, but okay, that's what it would be. Okay. Okay. And then okay. All right. Then remember we found this tangential acceleration by taking the angular acceleration and multiply by r. So we have the number that's right here. And for me, it's negative 6.93, okay, centimeters per second squared. Okay. That was the rate that was slowing down sort of in a linear sense during the second half of the story, which is also a plot graph like that. Right. Now, if you step back and look at it, and you compare the angular graphs to the linear type graphs, ooh, yes, what do you see if you compare these two? Are they the exact same shapes as each other? Is this shape, and so on?
Yeah.
Yeah, they match. Right? Now, of course, the vertical axes are different. They represent different variables with different units. Right? The time axis is, of course, the same. But yeah, the overall shape of each graph is also the same. Right? Uh, I mean, of course it should be, because mathematically, all we did to go from angular to linear is just multiply by r, which is a constant value. So for me, I just go from here to here, I just multiply by 11 centimeters. I go from the left graph to the right graph. So, do you think that's also going to be true for displacement? Yeah. There's some kind of distance graph, right? I bet it's going to be the same shape. I just got to get some numbers on here. So my initial distance was 207 centimeters. So, and it achieved that at a constant rate. So it's a straight shot to 207 centimeters. Okay. And then slowing down to a stop, it took an additional 67. If I do 207 plus the additional 67, that's a total of 274 centimeters. So go up to 274, and then put a point there, and it's just going to curve to a stop. Point, curve to a stop. Yeah, so same shape graph left and right. Oh, yeah. Okay. Now, on the puzzles that I gave to you guys, I was trying to find, of course, puzzles out of your book, and a lot of them are, but actually, the puzzles out of your book, there are some gravitation questions. I was hunting around, and weirdly enough, couldn't find anything on circular motion or centripetal force. So I don't know where they put that, or if they don't have it at all. So I just went ahead and copied something out of AP's book. Actually, a few puzzles. So that dark earth and background. Okay. But I think that you guys can solve these anyway. So let's see if we can knock out number 9 for the weekend here. Yeah, we'll just do this one. Right, so we've got this mass M1 going around a circle, and they gave you that as 0.125 kilograms. We've got a string. Ooh, there's a hole in the center of the table. And down in the other end of the string is hanging some M2. It says neglect frictional forces. They also gave you this radius. Okay, so they gave you M1 here, bing, M2 here, bing, and the radius of 1 meter in this case. All right, guess that. Man, this sure does look a lot like your guys' last lab. Okay, yeah, so you guys can hold on to this paper for next week, right? Because that aside, that different lab. So for that later. Here. All right. So get this here. We got this top block going around, and this is mass 1 equals 0.125 kilograms. It's on the string with a radius of 1.0 meters. And there's a hole in the middle of the table, and the string hangs down. And there's this other block of mass 2 is 0.225 kilograms right there. So that's the setup. So it says draw a free body diagram on both blocks. So to this bottom block, here, I'll give you guys one more number. Can you guys say G is probably about 10 meters per second squared? Okay, that would be good to know, right? Okay. Okay, so this bottom block has a weight. I'll call it mg. Okay. And what would that be equal to? Can I take this mass of 0.225 multiplied by this g at 10? How many newtons is that? 2.25 newtons? Is that right? 2.25? Okay. And then, ooh, is there a string tension pulling up? Okay. And Because if this bottom mass is not moving at all, then is the string tension, does it have the exact same force as this weight down here? 2.25 newtons? The same force, wouldn't it? Right. Now this block on the top, ooh, does that string tension transfer into the top block, pulling in, right like that? Yeah. And that's a tension force of course 2.25 newtons also. Right? And I bet this top block also has a weight and a normal force that are balancing out because it is on a table surface, although it is frictionless. But that's right. So I bet this weight is 1.25 newtons because mass and gravity. And I bet this normal force right here balances that out. Okay? Right, so there's the full diagram going on. Calculate the tension in the string. Well, we did that already. Okay, so part A says draw the free body diagrams, did that. Part B says calculate the tension in the string. So here's part B right here. All right, we already got that. Bing, done. 2.25 newtons. You guys already got that. This mass brings gravity down. The tension balances out, so it's the same value. So, okay. And let's see, calculate the speed of this block on the top. Okay, so this block on the top, it has some speed. So I can say that this string tension is providing a centripetal force, which works out as mv squared over r, like that. We're going to calculate speed. So let's pop some numbers in. So right here, I'm going to put in 2.25 newtons. The mass of the block, I'm going to put in 0.125 kilograms. The speed we're solving for, now it's squared, so we have to take a square root of the n. And the radius was given as 1 meter. Confident? And so I'm going to say speed is 2.25 times 1 over 0.125 square root of all that meters per second. So let's say square root 225 125. I'm getting 4.24 meters per second. I think that looks reasonable. Yeah. 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 I will post this recording to Google Classroom. Yeah, and you guys have a good weekend.